What reagent does that? Which direction are you trying to go? Left to right? Up to down? We're trying to end with what structure? The aldehyde. Lithium aluminum hydride does what? What type of reaction? Okay. Does reduction. So we've got to be careful that what we're looking at, and this is, I think the redox ones are particularly tricky because you look at what you've got written, you go, oh, I want lithium aluminum hydride because I'm going from a carbonyl to an alcohol. No, you remember you're thinking backwards. You're going from the alcohol to the carbonyl, which means you're doing an oxidation, which means either chromic acid or PCC. And we want to use PCC because why? We don't want to fully oxidize it. So we have done one step. I would argue you jumped ahead a little bit on me, but that's fine. Okay, look at the starting material. Where is it reactive? What functional group do we have in the starting material? Alkanes. Are alkanes reactive? No, there is only one reaction we can do with alkanes. What is that? Radical substitution, which is our Br2 and light. Instead of Br2, you could also use NBS. Both of those are fine. Where does that do the substitution? In the most substituted position, because that's where we form the most stable radical. Okay. I would jump straight to that, personally, because alkanes, that's the only reaction I can do. I have no other choice. So I would do that and get that down first, and now I could go back through. So now I've got an alkyl halide. Okay, so I can do pretty much substitution and elimination with the alkyl halides. Okay, my reactivity is going to be sitting on that tertiary carbon. Constraints on carbon sources, there are none. Okay, major functional group changes. I've gone from an alkyl halide to an aldehyde, and depending on what step of the problem we're looking at, either an aldehyde or an alcohol. Okay, since we're at this point, I would say we're looking at the halide to the alcohol. Okay. Identify the carbon skeleton. Has my carbon skeleton changed? No. It's actually entirely the same, which means my reactive carbon that I labeled in my starting material on that tertiary carbon is the same as the reactive carbon in my product. Okay. Do we have to move reactivity? Where's the reactivity in my product? It's on the carbon where our alcohol is. We look at our starting material at this point, we've got the reactivity at the wrong spot. Okay, so yes, we have to move reactivity. To move reactivity, we said really the only option we've got is to look at making an alkene. Because alkene functional groups have reactivity at 2 carbons. Okay? So what type of reaction am I going to run next on my starting material? I need to do an elimination reaction. What product do I want for my elimination reaction? I want an alkene where? Needs to be straight off the top. Okay, and this is now where we have to be kind of careful. What do we need to facilitate an elimination reaction? Strong base. Writing strong base probably not get you any points in this case. Okay, and the question becomes, yes, we'll talk about that too in just a second. If we do just a strong base with that reaction, we'll go through and do an elimination reaction, an E2 mechanism. The E2 mechanism forms the pi bond where? the most substituted positions, which is within the ring. Where do we want our alkene to form? Outside, our least substituted. That is challenging. How do we get our least substituted double bond? We need a strong, bulky base. Right, the one that we've talked about frequently in this class is frequently with my students, would be T-butoxide or tert butoxide. The one that you've clearly heard of before is LDA, which they're both very strong bases. The LDA is probably a little bit better, admittedly. LDA stands for lithium diisopropylamine. Yeah, I don't have a lot of space for it. Okay, there's our LDA. So it's a negatively charged nitrogen sandwiched between isopropyl groups. It's actually bulkier than our oxygen. Okay, and a stronger base because we have a negatively charged nitrogen as opposed to negatively charged oxygen. That will give us the Hoffman product, okay, our least substituted double bond. What do we do now? Okay. I want to run an addition reaction, and as a pseudo hint, we can probably get away with it in just one arrow. Okay. We're going to run an addition reaction here, where what am I adding? The OH, sure, and hydrogen. So we have to add hydrogen and OH. What's the natural way to add hydrogen and OH? H2SO4 and H2O. Don't write this down yet. And same as saying H3O plus. The hydrogen will get added to our alkene first, and it gets put on where? The position that has the most hydrogens, so that we form the most stable carbocation. Which means if we add that reagent, what we end up with, our hydrogen there, our positive charge inside the ring, which then ultimately picks up the OH. Is that the product we wanted? No. So this is where it's helpful to go through and check. Ignore what my product is and now just say what's going to happen. What happens is we put the OH in the wrong spot. Okay? So that doesn't get me there. So now I would erase all of that and I try again. Do I know of another reagent that allows me to add OH across a double bond? You've got the right idea with looking at peroxides, but we don't have that option. We don't have an H2O and ROR. Only one reagent adds hydrogen and OH in an anti-Markovnikov fashion. Mercuration still adds it in the standard fashion. I know, and this is where it's rough. You just keep running through all the reagents, particularly because you don't have them out in front of you. If you have them out in front of you, you can start to go, oh, okay, that's the one I need to use. But yeah, it's definitely going to be rough at this point. If you don't know the reagents, you're stuck. Okay, you don't really have a choice. Someone did mention it. I am being kind of mean, but they didn't say it confidently enough. You got to be confident. Reagent we're going to add are BH3 and THF. The first step of that results in putting the boron on the outside of the structure and the hydrogen on the inside. The hydrogen acts as our negative, the boron acts as the positive, so it matches up exactly as it should. Followed by second step of, this is where your peroxide option came in. Peroxide H2O2, OH minus, and typically I think you usually see H2O in there as well. They usually add a bunch of freaking things in there for some reason. But really all you need to see is the H2O2 and the OH minus. That then cleaves off the BH2 and takes it to our alcohol. Once we have the alcohol, what can we do? Add the PCC, and we now have our aldehyde. Bless you. So, only 20 minutes to do one problem. Realize that was 20 minutes of you staring at it and saying, I don't know the reagents. If you have the reagents in front of you, it should shorten your time drastically. Okay? So that's probably the best ways to pick up synthesis or reagents in general is just through synthesis questions. You keep doing them again and again and again. And you go through the same process that we just went through. Slowly break it down, identify your pieces, start to label through and see what you can come up with. I will try my best to build a generic synthesis practice assignment for Sapling and just get that posted. I will also try and organize it such that the earlier questions within the synthesis are things that you guys have already seen, and the later ones in the synthesis assignment would be ones that you would know by the end of the semester. Okay, I'll try my best at that, but I can't make any guarantees. That will not get graded. Okay, I'll try and flag that somewhere so you know where to find it and let you know. Okay.